Greetings everyone, good afternoon. I will continue this session with you. It's my pleasure to be with you today. And I will continue on the topic that we started in the previous lecture, going through the limits in multivariable functions. Remember in the previous session we took some notations first and some bullets. The first of them is the topological definitions. This is really a very important lecture, as it will give you, as I told you in the previous lecture, also some definitions about the neighborhood of a certain point, the closure, the internal of regions, external of A, and the accumulation point, the isolated points. All of this you will find them in the previous in the old lecture or by the beginning of this part. Then we went through the limits, the lateral limits of a function in one variable, and after that we went to limits of multivariable functions, directional limits through various curves, then limits of multivariable functions using the definition of Cauchy, and that was the heading of the previous session. We saw how to start working with epsilon and delta and start determining the inequality. Based on it, we will know the general limit of a certain multivariable function. Also, we ended the previous session by the iterated limits and the difference between it and the general limits, and this is really very important as we spoke in the previous lecture. Today I believe the last thing that we stopped at in the previous lecture was studying the limits using polar coordinates. This is really very easy topic to continue, and also it's deeply connected with what we had in the previous lecture. So I will start with let D be an open set F such that D into R and the AB is any point belongs to D. Suppose that there exists R, which is greater than 0, around the ball or the open ball B of AB with radius R, except at A or B, which belongs in D. Define the function. That's the definition of the function within polar. That's f of r theta, where the conversion from the x and y into the r and theta is going to be a plus r cosine theta plus b r sine theta. That's if you are targeting any point other than the origin, where r belongs to 0 and r the open ball in the neighborhood of the point that you are interested in, and theta is the angles starting from 0 and tends to 2 over pi. In order to determine limits in such case, we will have to be sure about this value, which is if we let R, let L, be one of the points or one of the values belongs to R, and if there exists M such that between 0 and R, the radius of the open ball around the point that you are interested in, where f of r theta minus L is less than or equal certain value, which is a function in R, let's call it NR, for every r and theta for the same conditions. If you find the limit of MR tends to 0, then the limit of your function equal to L. So actually, we need to be sure that the function equal to L. All I have to do is to take the function by itself minus L and try to check this norm. If it's correct and tends to 0, then your limit equal to L. Let's test this issue on more than one problem. If I went to the first problem, he is asking you about the existence of this function or of this limit, which states that I have limit xy tends to the origin, and for 2x squared y plus y cubed divided by x squared u squared, y squared. Usually I would prefer using polar coordinates once you find x squared and y squared. This is why, because x squared plus y squared equal to r squared, so it will make your life easier. As you can see here, the point that we are interested in is the origin, 0 and 0. So in this case, instead of having AR cosine theta for x, it's going to be R cosine theta directly, and for y, it's going to be R sine theta. So if I want to change into polar coordinates, it's going to be very simple. That's R cosine theta, and this is for every value of x, and every value of y can be easily changed to be R sine theta. Now I will start changing the values of these components. So I will start with x squared plus y squared, which is R squared. And then I will start changing the value on the denominator. So if you want to do it, I will do it with you, and then we will go through the slides. I will have the limit of x and y, which tends to the origin 0 and 0, for the value of the function, as you can see, 2 of an x squared times y plus y cubed divided by x squared plus y squared. I will take these values for the polar coordinates. Also, I know that r squared equal to x squared plus y squared, and since x and y tends to the origin, r will tends to 0. So if I start changing all the variables in my limit into the r and theta, I will find that I am working with limit r tends to 0 for the function. For the denominator it's simply r squared. For the denominator it's going to be 2. Replace x with the value, so it's going to come up to r squared times cosine square theta times r and sine theta, then plus sine cube of theta. Of course, I have r cube in here. So if I want to simplify things a little bit, I think we can take r here and r here, so it's going to come up to 2 of an r cube times cosine square theta times sine of a theta plus a sine cube of a theta, as you can see. And all of this is divided by r squared, and we are taking the limit from r up to 0. So all I have to do is to just simplify stuff. So eliminating r squared with r cubed, you will end up having a limit of r tends to 0. You will have 2r times cosine square theta sine theta plus a sine cube of a theta, which actually is an r, a function in r. So if I want to check limit limit r tends to 0 for the function mr, you will find it equal to 0, which stands for that this value or this function will already exist and it's equal to 0. So once more, we start replacing every x and every y by r cosine theta. So it's going to be 2r cosine square theta, as you can see. This is r sine theta, so we can collect the r's here. It's going to be r cubed, similar to this one. And now I can simplify it to be on this form, which actually stands that f of r theta, which is, as I told you, according to the theory, if I have f of r theta minus l less than or equal to mr, then the function by itself, and the mr equal to 0, then the limit already exists and it's equal to 0. I'm sorry, to l. So now I can find simply for limit r tends to 0 for the function by itself, it's gonna equal to 0 just from a direct substitution. So I know the limit for the time being, which is 0. Now let's check the existence of this theory as I told you. This is f r theta, which is r 2 cosine square theta, or r times some function in a theta, minus the limit. Now I know it, it's equal to 0, so this is 0. So f r theta which equal to an r equal to mr, taking the limit of this guy, which is limit of mr, which is gonna come up to 0 nicely and easy, then the limit of this function equal to a 0. As you can see in this problem, we didn't exert a lot of efforts. We started by just replacing into polar coordinates. The polar coordinates helped me out a large deal because I'm getting rid of x squared y squared and all the terms like this, and it's ended up really very nicely. Once you take r equal to 0, you will find the limit equal to 0, and once you start to substitute on the definition of the polar theory, you will find it straightforward. Let's try it on another problem. That's another problem, and also it's a very nice problem. Using polar coordinates, study the existence of the limit sine x squared plus y squared over x squared plus y squared. This is really very tempting because once you start changing the, you have the values of x squared plus y squared, which already exist in the sine and also in the sine function, and also on the denominator. So if I want to change this function, which states, this limit x and y tends to 0 and 0, and this is for the function sine of an x squared plus y squared divided by x squared plus y squared. So I will take the decision to change into polar, taking advantage from once x and y tends to 0 and 0, I will have r changing also into 0, and instead of dealing with x squared plus y squared, I will change them to r squared. So I will have now limit of r tends to 0, and this is for a sine of r squared divided by r squared. If you try to substitute in this limit, you will have 0 over 0, and that's a very famous problem, okay? And it had been proven that once you have a sine of an angle divided by the angle, this limit exists and it is equal to 1. So now I'm sure that L at the time being equal to 1. So once more, Ahmed, if I want to check the existence of the limit supporting the polar coordinates, it's very, very simple. All I have to do is to get the norm, which is simply, it's gonna be the f function of an x and y minus L, and try to check what's gonna be. This is really very simple because all the data is in front of you. So this is gonna lead to equal to 0, and simply means that f x and y equal to L for the limit of x and y tends to 0 and 0. Once more, I will try to check all of this with you with the slides. So now I will change to polar coordinates once more. I have x and y tends to 0 and 0, so I will have sine of an r squared instead of x squared y squared, and exactly the same with the denominator. But I thought just to replace it and show it for you as a step by step. So now I'm ending as sine over r squared over r squared, which once you substitute, it will confirm this famous limit, which is the sine angle over an angle. Once it is 0 over 0, I can't consider it equal to 1. So now I can use this limit for the time being, and I know that L now is equal to 1. If we start by the definition, as I told you exactly in here, so this is the value of function minus L. So f of r and theta minus 1, which is less than or equal to 0, it will equal to 0 directly, as you can see, because f of r theta is equal to 1. So once you substitute, you will find this equal to 0, which means the sine of an r squared over r squared or x squared plus y squared over x squared y squared is equal to 1. Straightforward, really very simple, but you will have to do the steps by your hand. This is the main theory about the polar coordinates, stating this is f of r theta minus l and r as we saw. And we can actually get this proposition out of this theory, which states the same results, but with a little bit switch, as we saw in the previous problem. So for the limit f of xy equal to L, if and only f, the limit equal to 0, this limit of xy minus L equal to 0, then the function by itself is going to equal to n. Even if you have f of xy minus L less than or equal g of xy, and this g of xy equal to 0, then f of xy also will equal to L. And this will help me out in a very nice problem like this one. He's asking you to check the existence of limit x and y tends to the origin. And you have 2xy tan minus 1, this is arctan of an xy minus x squared over the root of x squared y squared equal to 0. How to check this? This is actually a very nice problem because it will show you that I can take an advantage of my old knowledge in functions in general. As you can know, as you can see, or if we use Taylor expansion or Maclaurin expansion specific, as we are interested in point 0 and 0, for the part of arctan x, actually arctan x tends to be x for small values of the angle. So this is why I wrote you this statement. The main idea here is remarking that as the angle in arctan tends to 0, as the angle goes 0 or approaching the origin 0 and 0, the arctan x can be approximated to x. So I can replace arctan simply and mostly by x. That's the key fact here. Type digging in or from where it came, as x tends to 0, we will find that arctan x equal to x. This is going to give me a great fever because I can now replace arctan x plus y by x plus y. And then I will start simplifying all of this expression. So now, once more, using Maclaurin expansion on arctan x, once x in the neighborhood of x equal to 0, for the large terms of derivative x cubed over 3x5 over 5, and for small values of x, all of this will vanish, and the arctan x can be actually approximated to x. So instead of having arctan of x and y, I can use x and y. This is gonna make things a much easier task for me to simplify and to find the bound and to discuss the general limit of this function, as you can see at the coming lines. So first of all, now instead of dealing with 2xy arctan of xy, it's going to be 2xy times xy. And once you start substituting, the denominator, instead of having 2xy arctan, is going to be 2xy times x plus 1. So actually, this is the denominator that we are dealing with. 2 of an x squared y plus 2xy squared minus x squared. If we change into polar, it's going to be really very nice and smooth. So this is the function now, dealing with it instead of arctan. This is the final shape of this function. So instead of working with that guy, I will be working with this form, which is much simpler. Now, if I try to bound the results, I will find something very nice and logic too. This is, if I want to find the modulus of 2x squared y plus 2xy minus x squared, the modulus of these values, actually, it's going to be less than or equal. The first term modulus, the second term modulus or absolute, then plus x squared. So now I'm sure that this guy from the properties of the absolute function is greater than our denominator. So this function or this f of x and y will be now less than the value of 2x squared y plus 2xy squared plus x squared. Now I can take the advantage from the polar coordinates, changing the root or using the substitution that we used previously in the previous lecture, absolute x, which is less than r, absolute y, which is less than r, and using x squared, y squared under square root, which is equal to r, in changing this expression. So instead of having 2 of an x squared y plus, I believe, x y squared, let me just check for the values. This is also 2, and all of this is with absolutes and plus the last term, which is absolute of an x squared, and all of this is divided by the root of x squared plus y squared, taking the limit of x and y going to the origin. So this guy or this value, I'm sorry, this is the values, this is gonna be less than. I can replace the denominator by simply r. And the for 2 of an x squared and y, I can replace them by 2 of an r squared, but actually it's not gonna equal, it's gonna be less than or equal r squared times r, which means that this guy can be changed to r cubed. So instead of dealing with it on this form, it can be put on 2 of an r cubed plus 2 of an r cubed, and also now the result or the sign that will be used will be less than or equal. So I can start replacing, so it's going to be 4 of an r cubed, then plus r squared. This is the sign connecting those guys. This part of r can be simplified, so it can be less than, all of this can be less than or equal 4 of an r squared plus r simply. And for sure, this value is less than 5r cubed. For example, if I want to use the expression of r instead of having some value of r plus another value with different constants, I've considered it to be 5r cubed, and I'm pretty sure that this part, this left-hand side, is less than the value of 5r squared. This is exactly what happened here. X squared equal r squared. X squared y is r cubed, so replacing all these guys, you will have the following. This is going to be 2r cubed, r squared over r. Connecting these two guys together, or adding them together, and it's going to be 4 over r cubed. 4 over r cubed and r squared over r is going to be 4r squared plus r. All of this is still greater than or equal to your expression that you are working with. So I can consider this value, which is less than 5r cubed, for example. And now I know that as xy tends to an origin, r tends to 0. These are the results that we just reached. We will start using our inequality, which is f of r theta minus l, that's f of xy minus 0, which stands for this value, this guy. We have proved that it is less than or equal 5r cubed, which is 5 of a root of an x squared y squared, which can be considered as an g of x and y. And once you start, this is g of x and y. So once you take the limit of this function or of this part, you will find this part, of course, goes to 0, which means your limit is equal to 0, proved, and everything is very nice. This is actually one of the nicest problems that you can find. Now I want to speak with you about continuity. And as we initiated all of this in the previous lectures. We started by multivariable functions, definitions, shapes, functions, types of functions, and the shapes, the sketches, the details of all of this. Then we went through the gradient, how to find the tangents, and so on, and the normal at certain points. Then we went through the definitions of the limit of multivariable functions. Now it's time to study the continuity. Before we go to continuity in multivariable functions, I would like to remind you with the continuity in functions in just only one variable. It's very, very simple. How to be sure that this function is continuous at certain value. For a function f of x is said to be continuous at a certain points, these conditions must be satisfied. These conditions are simply, the function is defined, the limit of this function in the neighborhood of this point already exists, and the both of them equal to each other, as you already know. So first of all, f of a defined as a belongs to d of an f of x, the limit of the function already exists, and the both of them equal to each other. Once the definition equal to the value of the limit, then the function is continuous at this point. Also, to have a function which continuous at certain interval, it should be continuous at each point from the points that's connected to this function. You will have here more than one problem to study the convergence. Let's study the convergence of f of x equal at x, f of x equal x cubed at x equals 0. This is really very simple to check. All I have to do is to check that the function is defined at x equal to 0, and it's really defined at x equal to 0, y will equal to 0, so the value of the function is defined, it's equal to 0. Then I will try to get the limit of x cubed once x tends to 0, which will also already exist and equal to 0, both of them equal to each other. Then the function is continuous, simply continuous at x equal to 0. If I went to the other function, which is x squared minus 1 over x minus 1, I will be stuck first, or I will start first. I have x squared minus 1 over x minus 1. If you try to substitute, the value is not defined. If we try to simplify stuff and remove the singularity, it's going to be x plus 1. Using x equal to 1, the value is equal to 2. If we try to take the limit of x squared minus 1, the limit is equal to 2. So f of x is equal to a, and it's called a removable discontinuity of this function. If we want to go to discuss the topic of continuity over two variable functions at a certain point, this is going to be exactly similar to what we did. First of all, continuity of two variable function at a point. Let d belongs to r squared, x node y node is the point that we are targeting, and f from d to r. If the limit equal or defined, if the limit equal the definition of the function at this point, then the function is continuous. And in a similar manner, how to be sure that the limit already exists? It's very, very simple. All I have to do is to try to use the definition that we went through previously. That's for xy belongs to d, and for the norm or the magnitude of an xy minus x node y node, it is less than delta. And for this delta, which is greater than 0, there is an epsilon, which is f of xy minus L. Here, L is the value of the function at the point x node and y node. So I'm using this definition instead of L, which is less than epsilon, and that's the definition of delta and epsilon in limits, which is the Cauchy limit. If it's exactly similar to the functions in one variable, if f is said to be continuous on a set A, if it is continuous at each point at this point, relative to the domain of this function. I don't want to go further in solving more problems. I will leave it for next lecture, inshallah, and we will go through these list of problems, the limits and the continuity, of course, we will go through them. We have the general limits, we have the existence, start looking for the existence of these problems, and then we can discuss the continuity of these problems. I will leave this for next time. I will give you a chance to study all the topics that we went through, from the general limits definition, from the lateral limits, from the iterated method in evaluating limits, what the difference is, and so on. Please do go through them. You have a very good chance to go through all of this till our next time, and we will solve all of these problems. If you like to try them by yourself till we get together, this is also going to be great. Thank you very much for watching, and best of luck as usual. Thank you.